Okay, reinforcement learning. So what is this? So the setup we are going to have, I'm going to go in some detail with this, but the setup we have here is an agent that is going to learn by interacting with the environment. Okay, so we find this setup in video games, robotics, board games. There's a ton of different setups that we'll find that have found successful applications on this. Okay, what do we mean exactly by this? So we'll conceptualize this environment in the following way. We have an agent, which is going to be an AI, the AI that is going to be learning by interacting with the world. Okay, and the way the agent interacts is by taking some actions. These actions, as we'll see later, could be, for example, if you are a robot, the agent is a robot, it will be moving in the environment or taking things in the environment, right? Or if it's in a video game, it could be just pressing a button in the keyboard in order to interact with the video game. Okay, and from the world, the agent will make observations, right? The agent, if it's a robot and has eyes or has a camera, it will be able to observe what's going on around, and there will be rewards coming to the agent. Okay, so the agent will have some sense of what is good for him, and as you will see, as you can expect, the agent will try to maximize those rewards. Okay. Also, important detail, we are going to consider discrete timing. So all these will have a discrete time steps. So at time step 0, the agent receives observations and rewards, and by this information, the agent decides to take an action in the world. Okay, and the wall receives the action, something happens in the wall, right? And the wall produces a new observation and a new reward at time t+1. Okay, so there's going to be continuous interaction between agent and the wall. Okay, and an experience, we can consider an agent has an experience. How can we understand the experience through these concepts? Well, an experience is simply a sequence of observations, rewards, and actions. Okay, so and a sequence of this we'll consider this is an experience. Okay, so an important concept in reinforcement learning is the state. The state is the current situation of the wall, right? And with the given state, the agent will have to decide which actions to take, right? So we can conceptualize the state in this way. It's a function that depends on the whole experience in that sequence, right? And we'll make an assumption here that that state will only depend on the current observation. Okay. Okay, an example of this setup in a video game. Imagine that you want to play Breakout, and you want to design an AI that is able to learn to play Breakout by itself. Okay, so no one will tell the AI how to play Breakout. The Breakout, by interacting with the game, will come up with the strategy to play Breakout and be successful in this. So the agent, as we said, will have the ability to take some actions that will produce something in the environment, in the video game. Those actions will correspond, in this case, in this video game, it can only go right or left. Right? So the output of the agent is going to be, okay, now I move right, I move left, or maybe I do nothing. Right? And then the agent will observe something from the video game. Will get some rewards. Right? These rewards, in the case of this video game, will be the score. Right? So the agent will try to produce actions that maximize, that make this score as high as possible. That's going to be the goal of the learning. And at the same time, the agent will be observing the video game. Right? I put here 4 frames because in order to have a notion of the motion that's going on in the video game, you need more than 1 frame, right? So in this case of the video game, usually the agent gets as an input, as observation, multiple frames in order to capture the motion that has been happening during the game. So that's the basic setup of reinforcement learning, and now we are going to try to see how the agent can come up with a strategy to learn to produce actions. And as you can imagine, one option of an agent is a neural network, and the case we are going to study is that. We are going to see in practice, we are going to build a deep neural network that will learn to play video games at the end of this tutorial. Okay, so in the last few days, you have been studying supervised learning, if you haven't been before, right? So how this setup of reinforcement learning relates to supervised learning, the machine learning that you have been studying in the previous tutorials, right? So there is a relationship. So for example, imagine that you have a data set of dogs and cats. You have images of dogs and cats, and the task of the agent is to say if in the image there is a dog or a cat, right? The agent will learn with supervised learning, the agent is given examples of dogs and cats, each of them with a label, and the agent has to learn to produce the correct label for each image, for unseen images, right? So that's the paradigm of supervised learning. So you could see it in this scheme of reinforcement learning in the following way. The agent can take 2 actions, the agent can say, well, this image I've just seen is a dog, or this image is a cat. That would be the action. right? The reward will be the classification score for that particular image, right? When the agent says that's a dog, if it's correct, the environment, the world will say, well, yeah, you were correct or you were wrong, right? And the observation, of course, is the image, right? So there are two differences between this setup and reinforcement learning. One is the sequence here. The sequence of the experience is just one step, right? So the agent receives one image, produces one action, and it's over. Then you can restart a new experience, right? And one image doesn't depend on previous images. The data set provides images independently from previous actions. And the second difference is that there is immediate feedback. So when the agent says there is a dog, the wall immediately tells, okay, you were right or you were wrong, right? In reinforcement learning, this doesn't need to be the case. You might be playing a video game, you might be pressing left, you might be moving left, and maybe the score doesn't increase or doesn't decrease. So you don't have feedback immediately. The feedback will come later, right? You press buttons while playing a video game and the feedback comes later. So I would say it's a more challenging situation than supervised learning. Okay, let's go a bit more in detail about reinforcement learning. So concept of a policy, right? So the policy is a strategy to decide which action to take. And this will depend on the state. This will depend on the current situation that the wall is. So essentially we can define pi as a function that maps the state to a new action, right? We can consider there are two possibilities. One is deterministic, right? There is just a mapping. And the other is that there is some randomness in the policy, right? Depending on some situation that might be useful to consider some randomness in case you want to explore sequences that randomly, right? So, but the whole concept here is that a policy maps a state, current situation, to a new action, right? And another central concept in reinforcement learning is the value function, right? So we're talking about that the agent wants to maximize the reward, wants to get as much reward as possible, right? But what you don't want is to just maximize the immediate reward. You just don't produce actions to get just a reward immediately. You want that your reward that you get over the whole sequence is as big as possible, right? And we can express this in the following way. We can talk about the reward that comes at this time, at time step t, and the future rewards, right? Usually we'll consider that the current reward is much more valuable, or we'll consider more important as the future rewards by adding a weight, gamma, right? And this way will decrease over time, right? And there is an expectation here because we are not sure about the reward, right? This expectation, depending on which policy we play, and the wall will have more reward or less reward, right? So we will never be sure about what's the reward that we are going to get. So essentially, we have this value function that depends on the current state, and that measures what we expect we'll get as a reward if we are in that state. Okay, and just one that you notice the following thing, that this function, there is recursion here. So if there is the reward at this time, reward at future time steps, but all this here also defines a new value function, in this case at the state t plus 1, right? So the value function at state t starts at reward t, but here there is some recursion which appears the value function at state t plus 1. Also, if we introduce this probability, the probability of transitioning to a new state, given the current state and an action, right? So here there is some Markovian assumption, meaning that the next state will only depend, or it can be modeled only by using the current state and the action, right? So by introducing this and taking into account this, we can rewrite the value function in the following way, in a recursive way. So we have here the value function. Essentially, we put all this here into here, in this term here, and you can see that here it appears a new value function, in this case at the state t plus 1, right? So there is some recursion. The value function depends on itself at the new state. And all this here is an expectation, right? So we don't know what's going to be the state in the future, so this is in expectation, depending on the probability of transitioning. And finally, before Yen-Ling goes into the different methods, so a different, similar concept to the value function is the Q function, and essentially is exactly the same. The only difference is that here, this only depends on the state, right? And there is an expectation on the actions, but the Q function essentially is the same, but with an action that we already decided. We say, okay, what's the value, what's the expected reward if I am at this state and I take this action? Essentially, it's exactly the same as the value function, but without this expectation because the action is given. Okay, and as you will see later, this will be very useful to introduce DQN, the algorithm that we are gonna study with deep learning. So just as a small recap, in this crash course, yeah, go ahead. Yeah.
So the difference between the value function and the Q function, just to clarify, would be that value functions relate to the expectation of what the outcome of an action would be, and the Q function seems to be after the action has been taken.
Yeah.
Okay.
So it's the expected reward in this case. Also, the expectation takes into account the action, but here the action is given, is fixed. Okay, so but essentially, both of them measure expected reward. One given the action, the other without. So then, if you don't have the action here, you also have to put the expected action. Okay, that depends on the policy. Okay, just a recap of what we're saying. Reinforcement learning is trying to learn a policy that maximizes the expected reward. Right? These are the two concepts we introduced, and that's what we are going to see. Now Yen-Ling is going to give an overview of the big landscape of reinforcement learnings in the literature.
Yeah, so as a recap, we can take a look at this diagram. So in reinforcement learning, we have a reward model, and action. So that means there are several ways we can try to optimize to learn, to figure out what's the best policy to take under this kind of setting. And one thing, continue what we discussed about value function. What you can do is, when you have an expectation at each state, you can confound the expected value and then select the optimal policy based on the expectation. But sometimes it is not very easy to figure out what's going to happen in the future and then compute all the expectations. So some people may think, okay, what about we just optimize the policy first? So we just randomly sample or choose some policy, and then we optimize to go from the worst one and slowly move to a good one. And once the action works, I can get a reward and the good policy. And lastly, since we are interacting with the environment, and sometimes the world is simpler or easier, like you are playing games. So we can actually learn the rule, know the rule, and learn the interaction model or transition model in the simpler or easier to learn world. So once we learn the model, we know the transition, and then we can sample the action from the world model. So I'm going to talk a little bit detail about each of these reinforcement learning types. So first, value-based reinforcement learning. So it's built on top of the value function we just talked about. So I'll give some example about how to evaluate the expected reward at each state. So take this simple gray word example. So Minion, a cartoon character, he really likes a banana. So he wants to get reward to get more banana, and less likely if he gets less banana, he's not so happy. But sometimes on the way, he has an opponent will take all his banana, so he will lose. And then he probably less prefer this state. So now he's at the state T, and we want to estimate what's the expected value at this state. So let's take a look what's the policy, all the action he can go. So now we take a sample of the action from the policy. So now he can go up, left, right, and down. And these are the probability to select each action. So we can, from the table look up, we can see, okay, we have an expected value like 6 because it's more closer to the huge reward. And this one, even though there's an immediate threat, but the expected value probably not so bad because the future return to get banana is also high. So you can take some kind of a risk for this. So once we have this, as Xavier just said, we can compute the expected value from all the value from the next time step, and then to be the one we are going to use at this state. So to choose the policy, what we can do, how can we choose policy using these value functions? So one thing we can do is first evaluate the Q value. So here we're using Q value instead of just the value function because we're considering the action. So we want to know at this state what action is more likely give me the better return. And then once we have filled out all the expected reward for each of the cells, we can try to take a step to select the policy based on the Q values I know. So I choose the action, they have the better reward, expected reward from my current estimation. And then I get a new policy. And then of course, I can do this over and over again. Once we get a new expected reward, I update my policy. And I have a new policy, I update a more accurate reward, and then I can improve my policy again. And this is a really, this algorithm is called policy iteration. We iterative to find a good policy given the value functions of the state space. But as what we say, sometimes you don't really want to compute the expected value, especially when the state space is so huge. The actions or possible states, you cannot enumerate all of them. Or sometimes in robotics, you are dealing with the continuous world. So there's no discrete state or action space. And you cannot compute exactly like each of the continuous actions along the way. So people usually, in this case, people usually want to optimize the policy, the actions directly. So by selecting a policy, what we means is, given the state, what's the best action to do at this state? So how can we optimize it? First, we can directly parameterize the policy with some parameter theta. So the goal is to find a good theta that can give us a good policy. So let's take another concrete example. We want to get the minion want to get banana again. So initially, we have some policy like this. So this policy is a distribution which parameterized by the theta 1. So we know, okay, this policy distribution probably not so good because there's a threat on the way. But so we want to improve on top of it. So how can we improve? We need a way to evaluate how good this policy is. So one lesson we learned from the optimization function, optimization class, is we need to define an objective or optimization function, optimization objective to know how we are going to optimize to. So in this case, given we have the policy, we can sample separate a lot of trajectory from this distribution. And then from each of this sampled trajectory, we know the action, so we can exactly compute what the reward we will get along the way. So we know, okay, what's the kind of expected reward for this trajectory. And then, as what we do in optimization, to optimize this parameter theta will be an easier step. Oh, and as a side note, usually, practically, we don't compute against this distribution exactly because it is probably some really complex distribution and you cannot compute. So in practically, people just like sample like n samples depending on their computation power to get from the distribution to do the estimation. So you can see like you may have some other computational way to have a better estimation of the reward for this given policy. So to do optimization, to optimize on the theta, one way we can do is we take a gradient descent, but we compute the gradient with regard to the parameter theta and take a step to optimize the parameter. And then when we have a new theta, probably move a little bit more here, we can evaluate the policy again. And then again, we have an updated theta, and then we can evaluate back again. So we iteratively do this to improve the theta that parameterize the policy. So we may move from the initially this very poor policy to the one that is really optimized and short path. So this is a reinforced algorithm you may hear a lot of people talk about when they're talking about reinforcement learning. And in many deep learning approach, they are doing policy gradient or policy-based RL. They are improving on top of the reinforced algorithm. And finally, when we're talking about model-based RL, there are many situations like when you play Go or play video games, or like some simple navigation task, you know what's a rule on the road. So when these rules are known or easy to learn, we can actually learn the model of how the world performs. And to be exactly what are the model we want to learn, it's basically the transition from state to state, and what kind of reward we will get at each state. And of course, you can parameterize each of this with a function, with another function theta, so we can optimize using like neural network or other approximator. And to learn this model, actually this becomes a supervised learning problem, because from all the experiences, if we want to learn the reward, it could be a regression from the data points to the value of the state. And then once we learn the world model, we can select, how can we select the policy based on the known model? So one way you can do is something what we did before to compute the value function and the value of each state and select optimal action based on that iteratively. And another way people usually, many people do is, since we have the distribution, we can do some sampling to sample possible trajectory from the distribution, and then scoring them to find the best one. So for example, if you are in a state, you can expand what could be the possible future, and then to give a tree like this. And then you can evaluate each of a termination node to find what is the best path to go through, to get to the goal, and then select it. So this is three types of reinforcement learning most of time people are talking about. And in all this problem, actually we all deal with the exploration and exploitation dilemma. So for example, when you have a reinforcement learning agent, you're trying to learn a policy in this game and this game. Usually we will say, well, this is very easy. You don't need to explore, and you can know the rule and how to play, and that's it. But this one, probably not so easy, because you need to explore a lot more. For example, you need to explore to figure out what each of the sprites means, and for example, to get to the key and open the door. And these are also some composition of tasks, which probably not so easy to explore and find a solution. And also, you may need to sacrifice some short-term returns in order to find something big in the future. So for example, you may go to the path with school and you hurt some points, but you can get a key on the way. So these two trade-off is exploration and exploitation. And exploitation is use what's the best policy you already have, and then take action and do it using the current information. And the exploration is you will try to do something you're probably not that familiar with, or you haven't tried before, but you are going to use that to collect some information to see if you can exploit it in the future to get something big. And usually there are some approaches to trade off between these two. And sometimes people just do it greedily. So like you just add some noise
And every time you have like epsilon probability to choose something new, to try it out, to see what's, if you can use the policy or the state transition. And another way people do is to do probability matching. So instead of picking the action or policy, there's a highest probability. We are sampling from the probability distribution. So for those they are not the best, still have a way you can try it out. And another important idea is to question about RL is sample efficiency. Because you know when you are learning, you are actually trying to explore and try it out, and to get some data and some information to build the model or learn the policy. And there's a question, how many samples do we need to learn a good policy? Because we know in deep learning, you need to have a lot of samples to learn a good classification model. And in RL, probably even worse, because you will need to explore more and the learning signal is weaker because you sometimes get the reward at the end. So there are two different ideas about NRL for different learner. So one is on policy learner and another is of policy learner. And on policy is something like when we look at the policy-based learner, whenever we change a new policy, we need to generate a new sample to evaluate if the policy is good or bad. So every time you need to generate new samples if you want to evaluate the policy. And of policy is something like when we want to build the model of environment. You may just use whatever information you have, no matter if it's current or past, and then use that to build a good transition model. So if you put it in the spectrum, there are like some RL algorithm like model-based is very efficient, is more efficient in data and samples. And some methods like policy gradient, they need to get a lot of sample whenever we want to evaluate a new thing. But you may have a question like, okay, if this is not so efficient in data usage, why we still need a method like this? So to deal with different kind of problem, you need different reinforcement learning algorithm. So for example, in some problem, it like holding a cup. It is probably easier to learn, okay, you need to approach a car and move a joint and make a contact, the moving policy. And rather than learning the whole dynamics or physics of the environment between cup and your hand gesture and hand effectors. Yeah, so this is a brief discussion about different types of RL algorithms. But of course, there are several model families we haven't talked about. And one thing is people usually like trying to combine different types of reinforcement learning algorithms together to trying to get the best from like different words. So one example is the actor-critic algorithm you may hear from somewhere. So they take from the policy-based method, but instead of computing the exact reward for each policy, they also have a critique to learn the value functions of the current policy. So they will replace this one with a Q function or value function. And then when the actor decides to update the policy, they are optimized against the value to improve not just the parameter, but also the value function. And another type of thing is when we are talking about a different method, so basically we are optimizing against the value function, the policy function, or the transition model, or the reward model. And now with a deep learning with the deep learning, deep networks, we can also approximate all these kind of functions with a deep network. And one example you may like see before is DeepMind have a deep DQ network. You can use it to play the Atari game and have a very good score across several games. And now we will have Xavier to talk about what exactly they are doing inside the DQ network.
Okay, thank you. So as you can see, the landscape of algorithms in reinforcement learning is quite complex. There is a ton of different options and variations and so on. So we'll go through this particular example. This is a paper that was published in 2015 in Nature by DeepMind, and this started this big boom of reinforcement learning plus deep learning together. So we're going to go through the details in order that you have in mind, or that you could see one particular example of reinforcement learning. Okay, just a small recap. That's the last slide I showed before Yen-Ling took over. Essentially, value function is the expected reward, Q function, expected reward given a particular action, right? And we are going to, well, before working a bit with the maths, so the goal of this algorithm is going to be to pick an action that maximizes the Q function. So essentially, we want to find a policy that makes this Q function maximum, right? And we are going to call this Q star, right? So the policy that produces the maximum value. So that's essentially the maximum achievable value, right? If you have the best policy overall, that's the maximum achievable value you can have, right? And this policy, pi star, essentially is going to be based on picking the action that maximizes Q star, right? So at every time step, we're going to take, if we are able to have this or to estimate this guy here, every time step, we're going to take the action that maximizes Q star. Okay, how do we get Q star? First of all, we are going to work a bit more with the maths, just doing 2 simple steps, and then we're going to see that we can approximate this Q star with a deep neural network. The whole business of DQN is going to be approximating this with a deep network. So this is the previous equation I just showed, and essentially we want to find the policy that maximizes Q pi. And just by operating, you get that you need to apply a maximum on this guy, on the value function, and this is essentially equal to this. Just go quickly because I think the importance is what I'm going to say later. And essentially you arrive to this equation, which is also called the Bellman Equation. And essentially what you can see here is that the optimal policy, the optimal Q function essentially is also a recursive function, which depends on the Q function in the next state. Okay, so deep Q learning. Now here starts deep Q learning. That's the Bellman equation. There are many algorithms that are based on this, but what is particular of deep Q learning? So what deep Q learning says that we can approximate, or we want to approximate all this guy here with a new function, which is going to be a deep neural network. So we are going to use the same strategies as you have seen in previous tutorials, where you have a deep network, you show examples of, we'll see how we do this later, you show examples to the network, and the goal of the network is going to be approximating the value function, the expected reward. Okay, so in other terms, you can understand the Q function in the following way. It's a function that takes as an input the state, so you can enumerate all states, right, all possible situations in the game. Right? And for each of these states, you can take an action, right? And for this action taken in that state, you might get a reward, right? And the whole point here would be to play the video game, or interact with the environment, and we'll get examples in this table, right? We'll be getting examples, and with the deep neural network, we want to generalize across all this table, right? So we'll be given a training, some subset of this table, and a testing will be in a new situation we have never been, and through the deep neural network, we'll be able to approximate or generalize, hopefully generalize well, in that new situation, given the situations we have seen before. So F of W is the deep neural network. Okay? W are the parameters of the deep network. So we have this setup. We have our video game, we have a deep neural network. What we'll put in the deep neural network is going to be the last 4 frames, okay, in order to capture the motion, but essentially what we observe from the video game. And the deep neural network, the output of the deep neural network will be a set of neurons, one per different action. Okay, so if you have a game that you can move left and right, you will have two outputs here. Okay, so essentially you will map a set of frames to an action. Okay, and once you have this action, you will pick the best, the one that is maximum, and the one that is maximum will be applied in the video game. And then you will get new frames. From these new frames, again, you will do this over and over. Okay, now the whole question is, okay, how do I train this neural network? What is exactly the data? What is exactly my loss function that I want to optimize? Okay, and this guy, Watkins, in '89 proved that if you use this loss function, if your goal is to minimize this, I will explain a bit why this. If your goal is to minimize this, the neural network minimizes this. Over here, you have here square loss. Essentially, you converge, under some assumptions, you will converge to the optimal Q function. Okay, and what does this thing mean here? Okay, so first of all, here, what is important to note that this is the receive reward. So this is a situation that the agent has made an action, and just received a reward. Okay, and this is essentially the neural network, approximated by the neural network. Right? So we have all these terms, given the receive reward, this is the neural network, and the new state that has appeared after playing the action, and this is the neural network before playing the action. Right? So all these values, we have it, and essentially, this would be just a matter of minimizing this term. So why this function here? Why this terrible equation? So it's not so terrible if we look a bit more carefully. So if we go back to what it means this mathematically, this is the previous equations that I showed before, right? Again, this is approximated by the neural network, so the reward here is approximated by the neural network, and what you can see here is that there is this term here inside, so this is equal to this, and inside here there is this guy, and this guy is equal to this, right? So essentially, this one and this one cancel, there is a minus sign here, right? This expectation here doesn't apply because at this point we know the state, the next state, because we just played, so we have the state. So essentially, what we end up having is that when you do this minus this, you end up having the predicted reward by the neural network. So essentially, what you are minimizing here, what this equation is doing, is minimizing the real reward that you just get by the predicted reward the neural network thinks it's going to get. Okay? So when you calculate this, essentially what you are doing this, and this makes a lot of sense, right? So you want that the reward the neural network thinks it's going to get to be as similar as possible as the reward you actually just got. Okay, and this is also known, this strategy is known as minimizing the temporal difference error. Okay, so essentially that's what, when we do backpropagation, we are going to minimize this. Yeah.
So in the previous slide, you're always trying to minimize this difference, even though the real reward might be much higher than your predicted reward?
Well, this is the reward. What do you mean much higher than the predicted reward? Oh yeah. I think there are some strategies to. So, in practice, as you will see in the practical case, that's not exactly what is minimized. There is, in order to remove outliers, there is some nonlinearities applied here, but just conceptually, that's what we are going to do. Okay. So later you will see in practice that this is modified in order to avoid outliers. I think the case you just mentioned, right? When maybe the real reward is very, very different from the predicted reward. Yeah. But just for understanding, that's the theoretical goal. Then in practice, there are many hacks that are being applied, and in the code you will see later, that's one of the cases. Okay. Okay, just to insist one more, these Q functions here are neural networks, okay? So we have all this from the neural network. Okay, and the paper of deep learning, the Nature paper, so all this was already invented, so that was not in the Nature paper, that's not new in 2015, all this was already known there. There are two novelties in that paper that make this algorithm really shine in the video game setup. So the first novelty is the following one. So it introduces two neural networks. One, which is the target one, which is called W minus, they call it in the paper, and one is the actual one that you are doing backprop and you are updating at every iteration. So essentially, this one is, again, a neural network, that's essentially the same role, but they don't update it every time you have an update through the backprop. They update it every n time steps. And they argue in the paper that when they do this, they observe that the algorithm becomes more stable. Okay, so the argument why they introduced the change is more an empirical argument that they found that this tends to work well. Okay, Okay, so there are two networks. One is updated every time you get some sequence. The other is updated every n sequence, every n time steps in training. Another important component is what they call experience replay, right? So what they do in order to, instead of training with the last video games or with the last more recent experience that maybe all the sequences that you will be training are very similar to each other, what they do is they store in memory all the sequences the algorithm has been playing with. Okay, and then during training, they sample some of the sequences. In this way, you have a varied set of sequences which are different from each other. Right? So in this way, you have data that is more varied, and you break correlations between data, and they also observe that this produces a big improvement of the algorithm. And then just another detail, they also use epsilon greedy. This means that when the algorithm is playing, sometimes it doesn't follow the policy given by the network. Sometimes with a probability epsilon, it just chooses randomly an action in order to explore the different space much better. Okay, and now we'll go into the demos and the hands-on that you can see how this algorithm works in practice.
Yeah, so for DQN yesterday, I implemented DQN and have it to play Pong. So this is my agent left. So I can show you how it looks like now. Sorry. How can I move? I don't know how to move to the screen. Sorry. All right. Let me play it again. Uh-oh. Yeah, it is quite impressive, but it took a lot of training time. So yesterday, it took about 8 hours to get this kind of performance. So this, you will need some time to train the deep learning the reinforcement learning model, because you want to explore and collect the data. So one example we are going to have you to work on it is not this one, because it will take so much time to see the result. Instead, we'll have you to try a simpler couple example. It is a classical reinforcement learning example, and it is look like follows. You control a cart. You can go left or right, and there's a pendulum on top. So if you don't move, you will just fall. So you need to counterbalance it to make it step upright. So your goal is just to have it up as long as you want. And we can actually implement the DQ network to perform this task. And in this colleague example, I took it from the PyTorch website. How can I make it bigger? Is it big enough? All right. Oh, too big. All right, it's the right size. Okay. So in this tutorial, we'll go through how to implement replay memory and the DeepQ network, and what's the optimization methods, and how to train the network. And before that, because we are running on the Colab, there are a lot of things you need to do to set up the environment. But you can just ignore this cell, yeah, a lot of it, and jump to the tutorial first. So the first thing is we are using the OpenAI Gym. So there are several Atari games or several examples you can play around with. So if you want to try reinforcement learning in other examples, it's very, very easy for you to use. So here we are setting to use the carpool example. And to implement the replay memory, it is actually, you can consider it's just an array of relevant state and action pairs. So the memory, we implemented a few methods. So one is you want to push the new state or new experience into the memory. But because the memory have a capacity, so we always, when this is full, we'll rewrite the oldest memory. And then every time in training, we also want to sample from the memory to take into our training process. So there's also a sample method here. And for the deep Q network, we can skip all of this because we just talked about it. And concretely, it is a stack convolutional neural networks. So for example, here we have 3 convolution layers and go with a 3 batch normalization to have a better regularization. And we are going to use this to approximate the Q values. And then there are some input we want to extract from this environment. So first thing is the position of the carport, because you want to know what's the observation and the action, the result of your action. And also we want to take a screenshot to know what's the current gain state. So we take the image from the current, from the gain environment, they follow the actions. So this is one of the examples you will get from the screen capture. So there are some utility here because at each step we want to sample an action. So you need to implement this sampling function. And like what we just discussed before, there's an epsilon threshold. So there's a small probability you will try to explore other actions rather than choosing from your current policy from the Q network. And in the training loop, one thing to note is we have actually maintaining two networks, as Xavier just said. So there's one, the policy net, and another, the target net. So we will update the network after a few times to make the network more stabilized, the training process more stabilized. And then finally, this is the combination of all these components. So for each episode, you need to reset the environment, and then take the picture of what you have in the environment and the position, and then try to sample the action to follow it and evaluate using the network, and then do the optimization. So if you're running through the training process, not so many, and you can have a script to visualize what's your couple look like. And this is what I had with just 50 episodes. And you can try to play with different parameters and more complicated network to see how you can solve the problem. And as an exercise, you can pick whatever problem you're interested in from the OpenAI gym, or you can pick the one like mountain car. So the mountain car is very similar to the carport example. You control a car, but the goal is you want to go up to the hill to get to the goal there. And there's some momentum and how you control how much you want to accelerate the cart. You need to control. So with this, I think we are summarized with a few discussion topics. So people are always asking, where are the RL agents are so successful? What kind of cases they are working well? So far they are working well in many domains that we know the rules or simple rules or dynamics. So for example, the games, different type of games, video games, or simple environment. And another one is you can actually learn some motor skills from the role sensor input, but you need to give them enough data. So by enough, I mean, let's take this OpenAI dexterity example. They just come out several weeks. And if you haven't checked this blog post, you can actually read it after today and you will understand. So the goal is they built this robot arm. They can control, they can move the object and to control the object pose. And the goal of the robot is they will give the goal of the object pose. So you need to match what's your object at hand with the target goal they give the robot. So to do this, the robot needs to like explore to learn how to control the fingers and then how to turn the object over. And it is very easy for like human, but for this case, they actually train with 6,000 CPU cores and 8 GPUs to collect over around like 100 years of data in order to do the task. But the result is quite impressive, and we can take a look. Yeah. So this is a goal of the object's pose. And this is where the robot they train in the simulation, and then to turn the objects to match the one in the goal. And then you can have the robot to do it over and over again, because in the simulation they never get tired. So you can like just keep asking to do it and do it for 100 years, and then you can get pretty good results. So, yeah, they just swap the cube. Yeah. I think one important thing for this work is actually what they demonstrate is they train in a simulation. So everything they learn is from the simulation, and they bring the model to run on the real robot with a real object. But of course, in the simulation, they also build the network to recognize to predict the object pose, and also to learn the policy based on the object pose they have right now. All right. Mm-hmm.
So we're looking at the actual robot now, right?
Yeah, this is a retro robot, but they train in simulation.
But how many do they have to be trained on the robots afterwards?
One thing you can do is something like a fine-tuning. So usually people they train on the simulation, and you have a better you have a simpler rule to simulate the environment. And then you bring to the real robot, and then you fine-tune on the like real world noise in order to have the robot to adapt to those noises, and yeah.
You said that we center the screen around the rotation, around the pole.
Yeah.
Do we have to center it? Like when people train on Atari games, do they center the picture around the moving object, or do they just pick the screen?
Sorry, I didn't get.
The question is, do we have to center the image around the pole, or can we just pick the entire screen without telling the network where it should look?
Yeah, I think it's a later one. Yeah. Mm-hmm. Yeah. Okay, so finally, there are still some unsolved challenges that they are really interested in like a lot of people in the reinforcement learning community. So for example, the first thing is we know humans usually learn very quickly in the new task, but most of the deep RL agents, they usually slow or need many data. So most of the time we can only do it in simulation. And second is, as human, we can use like a previous knowledge to make like learning faster in the future. And then we are not really have good idea how to do, there are some like proposed solutions, but in general not a good idea to how to use the past knowledge. And another thing is we talk about like transfer to other tasks, or transfer from the simulation to the real environment. Or another thing we talk about to define like we always taken like reward function and reward value as a default thing we know. But actually we are not, it's not a good answer like how we can define a reward function. And sometimes there's not very good reward function in a task. And another is a composition of tasks. So like you need to combine different actions in order to achieve more goals. And there's no, currently not many RL agents can handle complex and composition of tasks. And there's also a lot of safety discussion about reinforcement learning agent. So like people are like, because the agent explore to learn the policy. So there's no control over like what kind of policy they learned, and will the policy help people or hurt the people. So there are several research topics working on this right now. And also there's also like a neuroscience or biology relationship between the reinforcement learning agent, like including like this different type of learning paradigms and how they actually implement it in brain. So like people are like interested in to figure out how they are related to brain and neuroscience or cognitive science. So with that, that's all our tutorial about reinforcement learning. And you can stay to like finish the DQ&A exercise, and we will be here to help you if you have any question, or like let us know if you have any question, and we will finish here.